Hello. In this video, we'll continue discussing about instruction pipelining. So before we jump into the details of pipeline design, just a recap of the notion of multi-cycle and pipeline and how they are different. So if you look at the multi-cycle design where one instruction can take multiple cycles compared to the single cycle CPU, but at a given point of time, only one instruction is in action. So, in that way, your overall IPC is limited by the number of cycles you take to finish a particular instruction. In contrast, when you go for pipelining, since you have divided the sequence of operations into different stages, what happens is when the first instruction is actually doing a decode, the second instruction can continue fetch. And similarly, when the first instruction is going towards, let's say, some later part of the operations, new instruction can keep on getting into the pipeline, right? So this way it improves the throughput in terms of number of instructions that getting pumped out per cycle. As you can see, after a period of time, every cycle you will see one instruction is getting like over, or they are done with their job, right? So this is the high level view in terms of difference between multi-cycle and pipeline, and you should not be confused multi-cycle as a way of pipeline. Okay, so this lecture will be the 5-stage pipeline and then what exactly goes through at each stage. So let's spend some time here. So the data path that we are seeing, it's actually from left to right, and apart from few which is actually coming from right to left. For example, this one and this one also, right? You may find some more, for example, this one also, right? But mostly the temporal order is actually left to right. The instructions are moving from left to right. So that's why the data path you can visualize that as a for data flow going from left to right in the pipeline. So the very first stage of the pipeline, as we have already discussed about the different stages in a single cycle CPU, though the notion of stage was not there because everything was happening in one single cycle. So to understand in single cycle CPU, so you start, let's say at time t. So on a positive edge, you start doing the entire stuff, right? From here and then like getting the data back, right? So this was happening in one cycle. Now what we have divided, the data path into multiple sub stages. So there will be few operations per stage, and the cycle length will be let's say defined by the length of a particular stage. Okay, so the first stage is instruction fetch, as we are all aware. So this is the operation where we are actually dealing with incrementing the PC. Okay, and along with that, the PC is going to the memory, which is called the instruction fetch. The memory is sending the actual instruction, right? So PC actually points to an address from which the instruction is there, and memory responds to the instruction. One of the additional things that you will see with the pipeline design is the notion of interstage pipeline registers. All of these. So these are pipeline registers, or these are also known as latches. Okay, because they are kind of latching the output of a previous stage and forwarding it to the next stage. Okay, so in a 5-stage pipeline, you will find 4 latches. These are also known as the interstage pipeline register or latches, right? So at the end of cycle 1, okay, so let's say this is cycle 1, the instruction is in this particular latch. Okay, along with that, the PC is also in this latch. In fact, this is PC plus 4 because PC is already incremented, right? Then the next stage come. Let's say this is cycle 2. And in cycle 2, the first instruction will start doing the register read operation and instruction decoding operation based on the opcode, bit of sign extension and other stuff, right? And in the meantime, the new instruction will come into picture, right? Let's say instruction 2 has entered into the pipeline, right? So this sequence goes on, and this is cycle 3, where the first instruction eventually performs some ALU operation depending on the source. It can be from the immediate values or from the register data that was actually stored here. So you will find all the register data stored here, okay? And eventually you go to cycle 4 for memory operation, and finally, once you have the data and you want to write back to the register, so then you come back and write into the register with the data, right? So these are the 5 stages. You can assume they will take 5 cycles for the first instruction, and then after that, every 1 cycle you will see 1 instruction is getting completed, right? So we will go through the data path in more detail with a bit of animation. Otherwise, this slides, the setup operation that I'm showing through this slide looks dense. So let's move on at the moment. So this is another way to visualize the instruction pipelining. And here we are actually showing the resource utilization. So resource are nothing but the different data path of different stages. One of the additional things that I have introduced here is the notion of instruction register IR. It's a register that stores the instruction that is coming from the memory. Remember, PC has the address. The address is fed into the memory. Memory responds with an instruction. So that is present in this instruction register. Okay. Rest of the things are more or less same. You will find latches, interstage latches. Okay. So the way to visualize the resources is, as I mentioned, right, from left to right, let's say the time moves. So at time t0, the first instruction is in fetch stage, right? And at time t1, first instruction moved to decode stage. Second instruction starts in the fetch stage. Time t2, the first instruction moved to execute stage. Second instruction moves to decode stage, and this is a new instruction which is in fetch stage. So this goes on continuously. And if you look at cycle number 5, which is T4, because you have started from T0, the pipeline is actually full. All the resources are getting utilized completely. And if you have like billions of instructions in your program, you will find that the pipeline is full all the time. Since here we are talking about only 5 instructions, I1 to I5, all the instructions will start committing slowly. So for example, you can see that at time T4, I1 is done. At time T5, I2 is done, then I3, then I4, then I5, right? So this is another way of visualizing pipelining in terms of the temporal window, what exactly happening per cycle. You can also look at this way, where you kind of populate all the instructions that are going through the pipeline in this order. So this is the sequence of instructions. Okay. And this is the time window. And whatever I have discussed in the previous slide, the same applies here. So you move from left to right. First cycle, first instruction is in the fetch. Second cycle, first instruction is in decode. Second instruction is in the fetch stage, right? And like that is, it goes on. So if you look at the first few cycles are actually filling the pipeline, right? And at some point of time, the pipeline becomes full, depending on the number of instructions you have. Here, in this case, we are considering a 5-stage pipeline. And then once instruction completes its write back stage, then that particular instruction is done, right? So then you're kind of emptying the pipeline. So these are the snapshot of any processor pipeline that you will see. Like initially instructions are coming in and then slowly utilizing the resources. Suddenly the resource utilization is 100%, and then they are going out of the pipeline. Okay. So now if we bring the notion of throughput, right? So if you look at here, now we have 5 instructions here, right? Instruction 1, 2, 3, 4, 5. And we are dealing with a 5-stage pipeline. Okay. So the first instruction itself takes 5 cycles to complete. So here K denotes the stage, the pipeline depth, or the number of stages. Okay. So first instruction is done in 5 cycle, which is the depth of the pipeline. And the next 4 instructions, since we are dealing with 5 instructions in total, next 4 instructions will take one additional cycles. Right? So they will be done with 6, 7, 8, and 9. So which means the total execution time is, for first instruction, it is the pipeline depth. Okay, so in this case 5. And for rest of the 4 instruction, right, n minus 1 is 4, it will take just 1 cycle. So in total, it's taking 9 cycles. Right? So let's revisit the notion of latency and bandwidth here. So as I mentioned in the last week, pipelining is a technique that improves the throughput. It may increase your latency, individual latency of a particular instruction, but it improves the overall throughput because our programs will have billions of instructions, and that's why throughput is more important, right? So, but hypothetically, if your program has only 1 instruction, then yeah, pipelining won't help. It will in fact make things worse. So let's take an example to understand what is the speed up that we can get from pipeline design compared to a single CPU design. So this is an example from the textbook itself. We are dealing with 4 instructions and 5 stages: fetch, decode, execute, memory, and write back. Okay. And each of the stages have different latencies. They are mentioned in nanosecond, right? So you can just add it up for each instruction. You will find a different amount of time. Okay. So in a single cycle design, what will happen is you will take 800 nanosecond as the cycle time. That is the worst case, longest instruction. And since you have 4 instructions, you will make it 800 into 4. That makes it 3200 nanosecond. Okay, so that's the total execution time or the latency, right? Now with the pipeline design, if we have a 5-stage pipeline design and the worst case delay per stage is, let's say, 200, right? So we come up with a 5-stage design where each stage takes 200 nanoseconds. So which means the first instruction will take 1000 nanoseconds, right? That's what we have discussed, because it will increase the latency because of the pipelining. But the rest 3 will be done in next 3 cycles, and where each cycle is actually 200 nanoseconds, right? So in total, we are getting 1600 nanoseconds for a pipeline design. So if you kind of try to find out the speed of, this is the execution time with the unpipelined, this is the execution time with the pipeline design. So it's kind of 2x faster, right? Now, if we kind of extrapolate it and make it more practical and try to find out what happens if you have billions of instructions. So let's say in single cycle, 1 billion instructions, each instruction will take 800 nanoseconds, right? So that makes it 800 seconds. But with the pipeline design, as we have already seen, the first instruction will just take 1000 nanosecond, but the rest of the instructions will take just 200 nanoseconds, right? So remember, we are dealing with billions here. So overall, approximately this number is closer to 200 seconds, right? So we are getting a speed of 4x. Another thing that we should keep in mind, as I have mentioned, in the pipeline design, you will find interstage pipeline registers or latches. We should include the latency that is coming because of the latch, right? So let's add that. So let's add 10 nanosecond for interstage latch. So now new clock cycle time in the pipeline design will be 210 nanoseconds. So previously 200 nanosecond was the stage delay, right? And plus now it is the latch delay, interstage. And overall, how many stages we have? So we have 5 stages. That makes it 4 interstage delays, right? So now if we try to complete the execution time equation, the first instruction will get completed in 1040 nanoseconds. Why 1040? Previously it was taking 1000, but now we have added 10 nanosecond interstage delay. So in a 5 stage, you'll have 4 interstage delays. That makes it 1040 nanosecond. And once you are done with that, the rest of the instruction will just get it done in 210 nanoseconds, right? So the first one will be 1040, and the rest of the 1 billion minus 1 will take 200 nanoseconds, 210 nanoseconds rather, right? So the new speed up will come in the range of 3.8x. So we are going down a bit, but still it's pretty high in terms of the throughput, right? 3.8 times faster with the pipeline design. Another crucial thing that we kind of left it in the last video is that how exactly you divide the data path, or how can you design a balanced pipeline design so that your throughput will be high. Well, that's the overall objective, that's the goal, right? So for example, suppose you have this data path, like accessing instruction memory is taking 10 units. Data memory, obviously, again, it will take 10 units because they are both memory. And let's say ALU takes 5 units of time, register file takes 1 unit, and your other data path, which are kind of doing some bit of rewrite, is taking 1 unit. Okay, it's basically the writing back into the register. So please remember, the slowest stage determines the clock in the pipeline. That's what we have discussed so far, right? So let's see how we can partition this data path. So if we go for a 4-stage pipeline, before going into the pipeline design, let's look at in unpipelined what will be the clock cycle time. So in the unpipelined, you have to just add all the latencies, right? So 10 plus 10, 20 plus 5, and then 1 plus 1, right? That makes it 27. So this will be the clock cycle time, right? 27 units of time. And if you kind of break it to all the data paths taking 5 units, it will become 25, and same here, right? Now, if I go for a pipeline design and I design a 4-stage pipeline, that means I'm kind of coming up with a data path that is spread across 4 stages, right? So as you can see, the slowest stage will be the memory stage, and that will be the clock cycle time, right? That will trigger that will actually define your clock cycle time. So let's have that, which is kind of giving us a speed up of 2.7, right? If I have the same 4-stage pipeline, but now the data path length has been kind of distributed. The delay have been distributed, especially the access to instruction memory and data memory, that have become 5 each. So that's why 25 by 10, it's 2.5. Right? So our speed up is actually going down. So remember, again, we are taking pipeline clock cycle as 10. Why? Because there are like 5 data paths, and we are using a 4-stage pipeline. So we have to club together 2 of them, right? There is no other way. We have to club together any 2. right, into one stage. Obviously, instruction memory and data memory can't be clubbed into one stage. Otherwise, as you have already discussed, it will create issue, right? Finally, if we go for a 5-stage pipeline, where each data path is taking 5 cycles or 5 units of time, and since we are dealing with a 5-stage pipeline, now each stage can be of 5 units of time, 5 units of time. So previously, remember, although all the data paths were taking 5 units of time, we have designed a 4-stage pipeline. So that's why we are merging 2 of the data path into one stage, and that's why the clock cycle time was 10 units. But now, since we are designing a 5-stage pipeline, the new clock cycle time is 5. So that makes it a huge jump in terms of speed up. We are getting a 5x, right? So if you look at theoretically, right, considering the ideal world, you will get a speed up of 5x if you are using a 5-stage pipeline, assuming the pipeline is balanced and then the latency and everything, no dependency at all. So the upper limit theoretically is 5 times. So if you have a k-stage pipeline, you can get k times speed up theoretically. Okay. With that, I will stop. Thank you.